got three different ways of communicating how the class did. And there's more ways that I could do this. I could get an average score and say average score for this class was whatever. This middle one is a breakdown of each individual student, and I put them in order. So you see the lowest score is 5, the highest score is 18, and you know, there were a lot of repeated results between 13 and 18. I can take that representation and I can turn it into a different kind of table called a tally chart, where I just go and I count up how many 5s and how many 11s and how many 13s and how many 14s I see, and that's turns into this picture, this chart, a table. I'm just literally counting how many 18s and 17s and 16s, etc. There's a way to do it with Excel, but unless you're doing big data sets, it's not really worth getting into that. And then this is a visual representation. And this is just a bar chart, standard bar chart. All I did was I highlighted this information, and then I went to insert and I made a little chart and I put in my title and my X and Y labels. So just from a consumer standpoint, which of these representations would you rather see in an article about how the students did? Or would you rather see this, the average score or the median score or something like that? What do you think is the best way to understand how the students did? Or do you think we need them all? You understand my question?
Is there a right answer, or is it just preference?
A lot of it's preference. No, there's no right answer. I mean, they're all three of these are the same in the sense that they are, you can look at them and you can get the information. None of them, I can't identify students based on this information. I can just see how the class did. This is a kind of a step further if I look at the average, because then I don't see the individual results. I just know that the average is 14.6, and there's a lot of different ways that might have happened mathematically. So that obscures the individual pieces of information. So we're going to look at, got a chat here. Okay. We're going to look at moving past bar charts and introducing another way of representing something, which is called a histogram. So let's move away from quiz scores and look at a sibling study. So in a past class, I passed around little pieces of paper and just asked people to write down how many siblings they had. And then I did that in a couple different sections, and then I put the information together. So this is a study of how many siblings people had. This is a bar chart. So I can look at the bar chart and I can say, one of the nice things about the bar chart compared to just a list of the information is that I can say the most common response was that people had 3 siblings. Okay, I don't know if that has any meaning or, if it's important, but the bar chart allows me to get that information quickly rather than looking at a big pile of numbers. Now, what we're going to introduce today is the idea of a histogram. Now, histogram is similar to a bar chart. They've got a lot of things in common, and they've got some differences. So this is the same information presented as a histogram. So you notice that one of the things that they have in common is that they're both made out of bars, rectangles. What do you notice that's different?
The combined ages, siblings.
Yeah, I did something down here with the siblings. I put them into ranges. So if you had 3 or 4, I put you together in the same group. If you had 5 or 6, I put you in the same group. That may not seem important here, But it would be really important if we're talking about income, because if you're talking about how much money somebody made, and one person made $41,000 and another person made $41,100, I don't really need a separate bar for those two people. They're very similar in terms of where they are. And if I have different bars for every single entry, my chart is going to get very crowded. And I might have gaps in between that are really meaningless. So grouping them together is a way of kind of condensing the information. Fewer bars, and kind of a more concise way of talking about it.
It's just like the way they would group for your what, tax returns, I guess.
Well, right. In income distribution is kind of a classic example of where we would use a histogram. Now, sometimes when you look up income distribution, they don't present it quite the way I would like to see it mathematically. For instance, you can kind of see gaps in these bars here, and there really shouldn't be any gaps. If it's a histogram, those bars should be touching each other. That's another big difference between representing as a bar chart versus a histogram. And if we zoom in on the x-axis, you can see that this, what I'm saying about the range of numbers, right? We don't care if you made $114,100 or $114,998, you're going in the same group. Because if we did it more specific, it would just be way too fractured. So it's a way of kind of smoothing out the data, grouping people together. And there are some choices that you can make in there that will impact the way that the picture looks. So the page 183 is the beginning of this section. And it just introduces you to the idea of this histogram. This is a histogram. The bars are all touching, and the x-axis is in ranges of years. That's kind of the really two important details about a histogram. Now, in terms of the age distribution, one of the nice things about seeing data this way is if you can imagine a list of all of the ages of everybody in the US, it's going to be a really long list. And this picture shows us something important, which is that up until, you know, age, what bar is that, 50 to 54, there's a pretty consistent distribution, which means a pretty consistent number of people in the US in each group. There is some variation, but it's really probably not that significant. Goes up, goes down. I mean, maybe there's some explanatory factor for why there's a few million less 10 to 14-year-olds than there are 5 to 9-year-olds, but probably it just kind of fluctuates around this level. Now, after this point, it does go down. That's easy to see too from the distribution. And that's logical because people die. They get older and they die, and the older you get, the more likely it is that you are going to die. And so these bars get shorter as we go off to the right. This is not technically correct in terms of a histogram because I shouldn't just lump everything together at the end. I should keep counting in terms of 5 years. Here, there's really no reason they couldn't have done that. It would have extended the graph maybe another 3 or 4 bars. I mean, what's the oldest person in the US? 105, 110? Not like it would be a ridiculous number of bars. In the case of that income distribution, there is a real logistical problem with trying to take the groups of 5,000 and continue going off to the right, which is why you've got these 2 lumps at the end. This set of people over here actually covers a huge range. This is 50,000 compared to 5,000, and then this is, I don't even know what the highest income in the US is, but it's way more than $250,000 a year. So you've got people, and I don't know how far this would extend, but it would probably go a pretty long ways off to the right. This is what we call the tail of the graph. This thing would extend this way and the bars would keep getting shorter and shorter and shorter. But because our graph has real physical limitations, we choose not to do that, or the authors chose not to do that. They put these two bars together. So this is called the tail. And the tail, I don't know if you remember from section 1, but the tail indicates something about whether this is skewed or not. The income data would be skewed right. Skewed right is a reflection of the fact that the average would be larger than the median. Note that the median here is not really in the center of the graph, especially if we brought this tail out to the right. Median household income is 50,000. I don't think the mean is reported on here, but the mean would be higher than that. And that's because of these people. These people are skewing the average, the mean, and making it bigger than the median because of this tail to the right. Okay, so what we've talked about so far is kind of moving from raw data, numbers, to a tally chart, to a bar chart, and then taking another step and kind of grouping that together to make what's called a histogram. Now, what we're going to be focused on you're probably not going to make your own histograms and normal distribution or distribution graphs in real life unless you go into something where you're collecting data and trying to process it and understand it. And I can't say for sure how much you're actually even going to ever look at data that's presented like this. It kind of depends on your interests and whether you seek those things out. I suspect that in mainstream media, that sort of thing doesn't pop up a whole lot. So where we're headed is something called the normal distribution. So here's some definitions that I think are important. A distribution is just a visual representation. It shows you the values that are more common. It shows you how the data is grouped. So I gave you some examples of that. So 3 siblings being the most. The way in the age graph, there was this sort of uniform number of people for the first 11 groups, and then after that it went down. A histogram is a specific kind of distribution where the x-axis labels are ranges of numbers instead of specific numbers. It looks like a bar chart, but the bars are right next to each other, usually touching. And where we're going is to talk about a special kind of histogram, which is a normal distribution. So a couple things to know about the normal distribution. The highest bar is in the center. So the mode is in the middle of the graph. It's symmetrical, so the left and the right side look the same. You take a mirror and you put it down the middle, it looks the same whether you're looking at the left or the right. And the last thing is this idea that the mean and the median and the mode are all the same. Now I'm going to get to the standard deviation in a second, but let's take a look at an example of a normal distribution. So that on the next page, they show you some different distributions. This is skewed left. This is skewed right. This is not any kind of pattern. And this is kind of what a normal distribution might look like, where this tallest bar is in the center, and then you have the symmetry, which means the left side and the right side kind of look the same. So the authors went out and they got some data to make a real histogram for you. They don't share this data with you, but they tell you where it came from, healthknowledge.org.uk. This is a histogram because it's a bar chart, but the bars are touching. The second thing about the histogram is not as obvious. which is that these bars should be a range of numbers. So in my histogram that I showed you the range for each bar. Here they've labeled the axis differently, and it's a little harder to tell, but we can work it out mathematically. So the first question I have is how, let me try to zoom in here. How many bars are there between, say, 2 kilograms and 3 kilograms? How many bars do you see between 2 and 3 kilograms?
Is
Seven.
it 7?
Yeah, it's 7, right? Don't assume it's 10. I mean, a lot of times you would have 10 bars between two things, but not in this case. If you count the bars, there's 7. And that's where the math comes in. We can think about each bar, and we can look at the range for each bar based on the fact that it's a ratio of 1 kilogram to 7 bars. Okay, so first I'm going to write that down. 1 kilogram to 7 bars is the ratio. I can interpret that. Let's go ahead and do the math. What's 1 divided by 7?
Zero point 0.14.
Yeah, it's not an even number, so we do have to do some rounding, but 0.14 will be fine. And then let's try to interpret it. For every there are see how your ratio interpretation skills are. All right, what do you think? What's that 0.14 mean? Remember the steps to interpret? Or is that so long ago that it's all gone?
Every 15 kilograms there's, I don't know.
Yeah,
Does that represent the kilogram?
Well, the top
For
number is
every bar.
kilograms. And we
For-
make, yeah, go ahead, Roger.
I was going to say for every bar, there's 0.14 kilograms.
Right, because the bottom number is measuring it in bars, right? Kilograms per bar. So that's for every 1 bar, there is 0.14 kilograms. So in other words, as you're thinking about these bars, this one would be from 2 to 2.14 kilograms. The next one's 2.14 to 2.28 kilograms. Then 2.28 to 2.42 kilograms. Then 2.42 to 2.56 kilograms, and so on and so forth until we get up to 3 kilograms. There should be 7 bars, and each bar represents a range. That's one of the things that makes it a histogram. Okay, so if there's a baby and it weighs 2.5 kilograms, where do I put it? in box 1, 2, 3, or 4?
It weighs how much?
2.5 kilograms.
Is it box one?
So
And box
2.5 is
one.
going to go here
that's
because it's between 2.42 and 2.56.
Oh, okay.
What if it's 2.2 kilograms?
box 2.
Box
And
2,
box
okay,
2.
good, all right. All right, let somebody else have a go. What if it's 2.01 kilograms? Where would the baby go?
And box 1.
That's good, Davida. All right. Leah, you want to give it a shot? 2.4 kilograms?
Is it box 3?
Good. So that's all that's happening in a histogram. I get these babies, I weigh them, and then I put them into the category that they fit based on their body weight when they were born. And the interesting thing is that it turns out that that's a histogram, which is a normal distribution. Now, I would say normal-ish because it's not perfectly normal. They overlaid this little bell curve on top of that to kind of show why this is normal-ish. It's not perfectly normal. Real data never is, but it's normal-ish in the sense that the highest bar is in the center. The mean, median, and mode are all about in the same place. Think about how I know that. The median is going to be in that center line, which is like here. The mode is the highest bar, that's there. And the mean is written here, 3.39. 3.39 is going to be in this bar, which is going to be right about there. And if we go up from there, we're going to hit the other line that I drew, if I can draw straight. Yes. Mean, median, mode, all in the same place. This is a normal distribution. And it turns out with normal distributions apply to a lot of different things in the physical world because variation is normal in the sense that the majority of people are in the center around the average, and then there are exceptions or things that are farther away from average, but those are less common, and so we get these tails that drop off. Our mathematical work is going to be about trying to quantify and use the normal distribution idea to just say things about populations. And I'm going to guide you through that, but the first thing to understand is what are we looking at here? Remember, this came from basically a list of 3,226 babies, and I looked at their weights, and then I put them into different categories based on where they fit. Any questions so far? Okay, we haven't done any math yet, except for the ratio, but that was just for fun, because I know you guys love interpreting ratios. Okay. So the next thing I want to talk about is standard deviation. Standard deviation is a statistical concept that's used to measure how things vary. And we haven't talked about variation really at all. We talked about measures of the center, we talked about the mean, we talked about the median, we talked about the mode. I did challenge you in Excel 3 to do a range calculation, and range is actually a measure of variation. Because if you have a high range, it means that there's a lot of spread in your data. The lowest and the highest are far apart, right? Because that's all the range is, max minus min. So standard deviation is just another way of doing that calculation. So before we get into these pictures here, let's look at numbers and think about it from a numeric perspective. So let me just try to explain what these numbers are. One of my main stress relief tools is I like to play Candy Crush. And there was a phase, I'm on like level 6,000, so don't mess with me. There was a phase in Candy Crush where they were giving out little striped candies randomly. It's supposedly randomly in these levels, and then you would get your striped candies, and then that would give you boosters and things. I don't want to spend money on this game. I just want to play the game. So because I'm a nerd, I started like keeping track of where I could go back and play earlier levels and get high numbers of striped candies to get my boosters and things. You can see some levels, you know, I would get 24 striped candies, 21. So those were good levels, and other levels weren't so good. And I started, because I was teaching this class, I started thinking about, oh, this is an interesting application of, you know, statistics, and you can look at this and think about normal distributions and things. So what I have here is a comparison of two levels. This is level 3,758 and then level 4,183. Don't worry about the 40%, the 50%. It's just kind of a number that I assigned to say how likely I was to succeed at that level. The average turns out to be the same. For the number of times I played it, and then I calculated the average, it turns out to be 7.8 for both of these lists, right? These are the individual games. So one time I got 15 candies, another time I got 9 candies on this level, 10 candies on this level, 3 candies on this level. So the point about the average is that it obscures the variation, right? I mean, if I can play this level and sometimes I get 13 and then sometimes I get 3, well, those are different outcomes, right? 3 candies is not as good as 13 candies. On average, I should get 7.8. I expect to get 7.8, and I've done it enough times to kind of expect to get between 7 or 8 candies, but that's not always how it works out. So the thing that the standard deviation does is it tells you something mathematically about the variation. Can you tell which of these there's more variation in? Which is there more variation? Like, which one do I see a bigger spread of results?
The first one.
Okay. Why do you say the first one?
Well, because it has more numbers, so that means, I don't know, you played more?
Okay. I did play that one more. That is, we can tell that based on that. It's not easy. I mean, variation, it's like, again, you're just looking at a list of numbers, and this is why we do things like distributions and averages and calculate standard deviation, because looking at a bunch of numbers, it's not easy to tell which one has more variation. If I think about range, remember range is max minus min, so equals max, I have Excel do it for me, minus min. Excel's pulling out the biggest number and they're subtracting out the smallest number. That's because the biggest number was 13 and the smallest number was 3, so the range was 10. Right? In the other one, I can probably just use autofill, move it over one. The range is 14. So that's evidence that there's more variation in the second one. And you might have guessed that based on the fact that I got 15 once, but I also got 1 once, right? So that was more variation than we saw over here. Now the standard deviation basically gives us the same feedback, which is that if we look at the standard deviation calculations, this one has a 3.8 versus this one, which has a 2.8. Bigger numbers, more variation. Higher standard deviation means the data is more spread out. More spread out means more variation. More variation means less consistent. There's times when you're interested in having more variation, and there's times when you probably want less variation. If you're in charge of a process that's supposed to produce something, you're probably more interested in consistency, which means you want less variation. And that, again, I've never worked in any kind of manufacturing setting, but I can imagine there's some applications there of thinking about standard deviation. Okay, now let's go back to this picture here. This is a visual representation of that. These are 3 graphs. They're all histograms, and they all basically are the same thing, which is looking at 100 years of information. How warm was it in September in 3 different cities in the US? You got Indianapolis, you got San Diego, you got Austin. Now, they're claiming that all 3 cities have the same average. I think, in fact, there's a little more variation than they're showing, but the point is that they're all similar averages. But the variation is very different, which is a very different experience in the cities. And the question is, can you tell which one is more spread out from the picture? Right? Now, we're not just talking about numbers. We went to the picture. We can see some numbers in the graph, but we can't see any individual numbers. What we're seeing is a distribution. So can you tell which one is more spread out?
I would say Indianapolis.
Okay. And why do you think that? What is it about
Just
the
because
picture
it's-
that makes you think that?
To me, just because they're ranging from different temps, a lot of different temperatures.
Okay, good. I
Um,
like the way you use the word range, because you've got these really low numbers. The bar's not big, but you did have some temperatures in the 30s, which is
Right.
But
Right.
you also had some temperatures in the 90s.
Mm-hmm.
And if you compare that to San Diego, it doesn't look like there were any days that were in the 30s in San Diego, nor were there any days in the 90s. So San Diego is more concentrated around the center, and Indiana is more spread out. That's exactly right. You get more variation in Indianapolis than you do in San Diego, and Austin is somewhere in between. Okay? So you can imagine why that would be interesting to you if you were planning on taking a vacation and you cared about the temperature. This might be some information that was useful to you. There's probably a lot of other things that you would use to make your decision about where to go that are not temperature based, but you can imagine how that might have some role to play. Okay, let's do one more practice on standard deviation. Okay. Can you tell which one is more spread out? And therefore, I want you to predict which one has a higher standard deviation. And again, not easy here because just looking at a bunch of numbers, they both have the exact same average. All right, what do you think? Let's call it B or C. Which one's more spread out?
I would say C.
C.
I got some B's, I got some C's. If B is more spread out, then which one would have a higher standard deviation? Would B have a higher standard deviation, or would C have a higher standard deviation? Let's go back and look at that picture. Indianapolis was more spread out. What has a higher standard deviation? Or this one. These are my standard deviations. Which one was more spread out, and which one had a higher standard deviation? Well, I guess I said it right there. The higher standard deviation means more spread out. So if B is more spread out, then B would have a higher standard deviation. And the opposite is true, which means that if C is more spread out, then C would have a higher standard deviation. So the standard deviation is going to tell us which one is more spread out. So we look at these numbers, and it turns out that C is more spread out because it has a higher standard deviation. So this is an example where that's a little hard to tell. Unless you
So
kind
will
of,
we, will,
yeah, go ahead.
will we ever be able to tell just by looking like, just because I say C because I see the 1,000
Mm.
and I remember, you know, you going back when we just said, when we seen another low number. So that's what really caught my eye, was looking at the 1,000. So will we be able to just figure it out that way, or?
Well, there's nothing to really, I'm just trying to get at a concept
Okay.
that if the standard deviation is higher, it's more spread out. If the standard deviation is lower, it's less spread out. You're never going to need to do anything like look at a data set and say about its variation or its spread in real life. I wouldn't imagine. There's a conceptual connection coming when we talk about poles and margin of error that I'm going to try to help you understand why it's significant. But so far, all we're talking about is concept here. Okay, so let's put our wheels on the ground. One of the things that we want to do is we want to be able to say some things about a normal distribution. This is called the empirical rule. This is on page 192. And it basically works like this. If this is a normal distribution, you can mathematically show that 68% of the population is within a standard deviation of the center, 95% of the population is within 2 standard deviations of the center, and 99.7% of the population is within 3 standard deviations of the center. Okay? First, I want to explain what that even means by going back to our birth weight example. So here's this thing which was normal or normal-ish. And when we say the empirical rule, what we can do is we can basically come up with 3 sentences that express something about babies. So I'm going to build the sentences for you, and then you're going to do some practice on your own. And this is starting to get to the point where you're doing the math that you need to be able to do. So go ahead and write down the mean and the standard deviation that's given to you on the side here, as you're going to need those numbers. And then I'm going to show you how to template out the sentences that you're going to make. Okay, and again, you can be working out of your book. This is page 189. Okay, you got the mean and the standard deviation written down? All right, good, because I'm going to need it. So the empirical rule ,68% of babies are born between, and this is where the math comes in. Very straightforward. What was the average baby's weight?
.39 kilograms.
Okay. So the 68% rule says within a standard deviation, and the standard deviation was 0.55 kilograms. So basically I go up and down the same amount. So I go 3.39 minus 0.55, and I go 3.39 plus 0.55. That's it. That's all the math you got to do. Oops, I forgot my equals. Okay, so now that's how I'm going to finish this sentence. So 68% of babies are born between 2.84 kilograms and 3.94 kilograms. That's the 68% statement. Where did it come from? Well, a lot of it was template. 68% of are between and That's the template. Where do the two numbers come from? They come from that minus plus action. Where does the stuff in the middle come from? Well, it's the context, right? What we're talking about here are babies and their weight, so I'm just trying to make that clear when I'm making my sentence. So the next two sentences are very similar. 95% of babies are born between. Now, when I do my next calculation, I'm just going to repeat my subtraction, okay? So you can think of it as kind of a little scale. In the middle, you have the mean. Then you do -1 standard deviation. No, I'm really sorry that I let you correct me. Okay. My goodness, that's not what I wanted to say. -1 standard deviation took me down to 2.84. Minus another standard deviation takes me down to 2.84 minus 0.55, so 2.29. And on the other side, I've got +1 standard deviation. That takes me up to 3.94. If I add another standard deviation, now I'm at 3.94 plus 0.55. So how would you finish the sentence? 95% of babies are born between
2.29 and
Yep.
4.49.
Okay, so where do those numbers come from? That's 2 standard deviations up and 2 standard deviations down from the center. I'm basically drawing a box and I'm saying, okay, how many babies am I going to find between these two numbers? And that's what the empirical rule is telling us. You always get a question at this point, like, where did the 68% come from? Where did 95% come from? I can't explain that to you because it requires calculus and integration. And you want to stay sane and also not, be 95 years old before you get to the point where you can make sense out of it. So I just ask you to accept that those things are the right numbers. Your job is just to build the sentence, to be able to look at a situation and say, okay, well, if that's a normal distribution, that's my mean, that's my standard deviation, 68% of are between and . Okay, go ahead and see if you can do the last one on your own. You got to go one more standard deviation to the right, and you got to go one more standard deviation to the left. So I'll set it up for you. You got -3 SD here. You got +3 SD here. You got to figure out these two numbers in order to finish that statement. Okay, what you got? 99.7% of babies are born between
1.74 kilograms and 5.04 kilograms.
Okay, pat yourself on the back. You sound pretty smart. Talking about standard deviations and normal distributions. Okay, that's half the battle. And obviously, we need to practice it, but that's the concept. Now, I always like to try to reinforce this concept by going back and thinking about how that applies to this actual situation. Let's just do the 68%. 2.84 and 3.94. 2.84, 3.94. I'm going to zoom in a little bit, and then we're going to mark this picture up. Okay, 2.84 would be right about here, I'm going to guess. Remember, these are counting by 0.14. So 2.14, 2.28, 2.42, 2.56, and then the next one would be 2. Oh, no, it would be this one, 2.84. Good thing I double checked myself. Okay, 3.94, which was the other number, right?
Yes.
Would be here near 4. Okay. Now, what I like to do is I try to count how many babies we have. How many babies are in this bar? How many babies are in this bar? How many babies are in this bar? And to do that, you've got to read off of the graph, which I think is good practice for just, you know, being comfortable with graphs and how to make sense out of them. The problem is we don't know how tall these bars are because we weren't given the actual data. So if I had a flat piece of paper, I would take a ruler or something and go across. Oh, maybe I can actually draw a line. Let's get fancy here. Boom, line. Ding. Aha. Okay. So what I want you to do is I want you to estimate how tall these bars are. And I want you to add up all of the babies in all of these bars and draw lines across to help you. Now it's a pretty big scale. I mean, if you look at the frequency on the left, they're counting in 50s basically, because the marks are hundreds, but then there's another kind of halfway mark there that you can use. I think that's all we need. You got to read those 7 numbers. So try to estimate, what do you think those 7 numbers are? I'll give you a minute to do that. The idea is that this should be about 68% of all of the babies in our study. That's what we're saying when we say the 68% rule. We go from the center, down 1 standard deviation, up 1 standard deviation. We draw a line. We look at all the babies in between. Okay, let's start listing numbers here. See if we can agree on our numbers. Let's start from the bottom. What do you think that first number is? 100 and
The 199.
199? I mean, it's pretty darn close to 200, right? So that seems like a reasonable guess. What about the next number?
206.
Okay. I'll take it. What about the next number? So now we're past 200, we're past 250, we're getting close to 300, but we're not there yet. What do you think the next number would be?
282.
Very specific. I like it, Roger. And what about this next one? Getting closer to 300.
$295.
Sure. Okay. We don't know. We're estimating based on what we see and how we drew these lines. Okay. Then we're going above 300. We're going above 350. So in this last set of 3 bars, oh, there's one that I didn't draw all the way across. I'm gonna need to get that one in there. Hold the phone. Let me draw one more line.
I'm confused. I thought you did.
This one on the back side.
Oh, yeah, that's right.
So that's not above 350.
Mm-hmm.
Okay, so let's continue on. What's the next number up? Somewhere between 300 and 350 and closer to 350.
About 330. Or 340. Matter of fact.
Okay. And then the next one up is above 350, but just barely. So maybe 351.
Mm-hmm.
Okay. And then just a little bit above that.
53.
53.
Okay. And then let's kind of get some perspective towards the top. I really want to zoom out because all my lines are matched up on there. 360. Okay. Okay, go ahead and add up all those numbers. Let me try to move this to a place where you can see it. That's 4 numbers, and then you got 4 more numbers. Okay, you got a number?
2,376.
Okay, what do you guys think?
That's what I got.
Okay. So let's think about whether that represents 68% of the babies. So how many babies are there total? There's a couple ways we could think about it. You got to bring percentages in here. There's a number on here that tells you how many babies are in this graph.
Is it n equals 3,000?
N equals 3,226. Okay, so let's do the math. What is 68% of 3,226? You can use a proportion, you can use just the decimal approach.
Is it 2,193.68?
You guys agree with that?
Yes.
0.68 times 3,226. Okay, so in other words, we would have predicted there to be about 2,194 babies in that center part. What we actually found was 2,376. So we're a little bit off. But remember that I was trying to be honest with you, this is normal-ish. This part in the center is probably higher than it should be if it's a true normal distribution. So we have that kind of overrepresentation in the middle. But the point is that mathematically, we can kind of make this general statement, the 68%, and we can convey a sense of what's happening in this picture. That's the idea. Okay. Another way that you might be asked to communicate that's not using this empirical rule is using a percentile concept. So the percentile concept is one you may run into in the real world if people talk about your baby's height or their weight in the doctor's office. Say a baby is in the 95th percentile for their height or length or whatever they call it for babies. I guess they're laying down. What does that mean? Well, it's related to this idea about the normal distribution, and it's basically the way to interpret that is that the baby is taller, longer than 95% of the babies in the population. So some important percentiles would be something like the 50th percentile. That's the median, because a baby that's bigger than 50% of the babies in the population is exactly in the middle. In XL2, I think you ran into some percentiles because they were talking about quintiles and quartiles and things like that. Those are just fancy groupings of, say, 10% or 20% or things like that. A quartile is 25%, a quintile is 20%, a decile is 10%. Again, you don't really run into those words a lot in the world because they're kind of technical words, but and you're not going to be tested on the quartile part. Right? It is fairly common to see something about a percentile and then translating that. So we'll come back around to that and how it fits in mathematically to a process. But the interpretation part is pretty simple. You just change the percentile into a percent and you say the baby is bigger than or taller than or whatever. Okay, so let me give you a practice problem and then we'll go on to the next part. So let's take this manufacturing situation. You got a machine that's, you know, obviously you got your popcorn popper and then it kind of bags up different machines, and the goal is that on average you're selling a bag that's a kilogram. So in a manufacturing process you might look at a test sample and kind of run the numbers and see whether you're living up to the promise to sell this much product to people. So what are you doing here? Number one, you're taking the average and the standard deviation and you're going to build this picture. So when you build this picture, they've already drawn this for you, but you draw the curve, you put in the center line, that's number 1, and then you go 3 to the right, and you go 3 to the left. Now, what number are you going to put on the center line? What's the number that should be in the middle?
$50.
Nope.
The 1,400. Well, the 1,040 grams.
1,040, because it's the average, and by average they mean mean. And remember, for a normal distribution, you should have the mean, median, and mode all in the center of the graph. So what you do is you start with the mean and you put it in the center. From there, you count to the right and the left in 25-gram pieces. So you go plus 25, plus 25, plus 25, minus 25, minus 25, minus 25. Okay. Go ahead and do that. And then try answering question number 2. That's an application of the empirical rule. Okay. Give you a minute for that. Okay, so 1,040 is in the middle.
I have a question.
Yep.
To find answer number 2, do you have to subtract and add from both sides of 1,040?
Let's start with the picture, because the picture is going to be helpful in terms of seeing what's happening here. So as you went to the left and to the right, what were the numbers that you got? We're counting in terms of standard deviations, starting with the mean in the center. And we add 1 standard deviation. Then we add another one, then we add another one. So what's this next number?
1,065.
Yep. Next.
1,090.
Yep. And then
1,000.
1115, right?
Mm-hmm.
Okay. Then going the other way, 1015,
990.
990, and then 965.
Mm-hmm.
So again, I'm going to try to draw this normal distribution here. Much easier to do by hand. Don't worry about things looking beautiful. The point is that there's 1 line in the center, and then there's 3 lines to the left, and there's 3 lines to the right. Okay. So this is the scaffolding that I recommend when you're doing these problems. Just draw a picture. Now, there's one where they, on the test typically, where they actually give you the blank drawing and you're supposed to fill in all of these numbers. But even if it doesn't give you that, I recommend that you do it because it's a nice way of kind of thinking about it. So, Roderick, your question was about question 2, which is the, how do I stop drawing? Which is the 95% rule. Because it's saying what's the 95% in the center? So 95% of blank are between blank and blank. That's the template you should be kind of thinking of. So what are we talking about here?
Popcorn.
Bags of popcorn, good. So 95% of the bags of popcorn are between, and this is where you have to connect the 95% with how many steps you're going. So 68% is one step or one standard deviation. 95% is two steps or two standard deviations. And 99.7% is three steps or three standard deviations.
Oh, okay. So we have to use that chart you gave us at the beginning. I get it.
So we're trying.
So
Yep, go ahead.
95% of the bags of popcorn are between 990 kilograms and 1,090 kilograms.
And I think there are grams, not kilograms, but
Oh,
that's
sorry.
the right, that's the right idea. Those would be heavy bags of popcorn. So that's what you want to be able to do. You want to be able to start with the mean and the standard deviation and create a little drawing and then come up with some kind of statement about 95%, 68%, something like that.